Okay, so I'm back in college today, so if you hear any traffic noise, that's because I'm in the lab today. So today we're going to look at the second part of our topic of haloalkanes. So yesterday we looked at how to prepare haloalkanes from alkenes, and the new reaction we looked at with alcohols and sodium halides and concentrated sulfuric acid. And we're going to look at the main reaction of haloalkanes today, and that's hydrolysis. So we're going to focus today on the mechanism, and we're going to look at the rates of hydrolysis in another video. So hydrolysis means the breaking down. Lysis means to break or split, in fact, with water. Okay, so hydro means water, and lysis means to split. So hydrolysis is the reaction where a covalent bond or covalent bonds are broken. Okay, so you must mention covalent bond in the answer for the exam, and this is broken through the reaction with water. So in the hydrolysis haloalkanes, we have the covalent bond between the carbon and the halogen being broken, and it's replaced by the hydroxyl group, and this hydroxyl group comes from the water, and the byproduct of this reaction is a hydrogen bromide. So this is effectively the reverse reaction of preparation of haloalkanes from alcohol. So the reverse is the alcohol reacting with hydrogen bromide to give us the haloalkane. So this is the reverse reaction of the one we saw yesterday. The problem with this reaction, it is very slow. So if we just use water with the haloalkane, this is a very slow reaction. So it wouldn't be a good reaction for us to do in industry if we want to produce our products quickly. So what we do instead, we use an alkali, so something like sodium hydroxide, which contains hydroxide ions, and the hydroxide ions is a better, what we call a nucleophile, so it would attack the haloalkane and react with it much quicker than water. Water is a poor nucleophile, and I explain what we mean by a nucleophile when we look at the mechanism next. Before we do that, you can see that we can write this equation, we can write the reaction in two different ways. We can write it with the sodium hydroxide or potassium hydroxide, or we can just cancel out the spectator ions. In this case, it will be sodium. We can cancel those out, and we get the ionic equation here. And to do this, we need to heat it to increase the rate of reaction. So the mechanism for this reaction for the hydrolysis of haloalkanes is called nucleophilic substitution. So a nucleophile is defined as an electron pair donor. So remember, electrophiles were electron pair acceptors, nucleophiles are electron pair donors. So here are some examples of nucleophiles. So water is a nucleophile because it can donate its lone pair in a reaction. Hydroxide ions are better nucleophiles, so this is why we use hydroxide ions in hydrolysis rather than water. It is a better nucleophile, or a more potent nucleophile, or a stronger nucleophile, because it has a full charge. Okay, so it's much more attractive to positive centers or partial positive centers in a reaction. So as you can see, nucleophiles do not have to be ions. We can have molecules with lone pairs, and they can donate lone pairs and act as nucleophiles as well. So if you're a second year, you know that ammonia is the nucleophile in nucleophilic addition in making amines. So I'm going to show you some examples of nucleophilic substitution mechanisms. And here we have a haloalkane. This is bromopropane. And here's our nucleophile. This is the hydroxide ion, which is a more potent nucleophile than water. So as you can see, the functional group here on the haloalkane is this halogen group, and it is reactive because there's a dipole along this carbon bromine bond. So we have a partial positive on the carbon and a partial negative on the bromine, because bromine is more electronegative than carbon. So bromine would attract the bonding pair of electrons towards it greater than carbon. So the partial positive carbon on this haloalkane is what's attracting the nucleophile, this hydroxyl ion with the lone pair. So we can draw an arrow to show the movement of electrons from that lone pair, from the charge on the hydroxyl ion to the partial positive centre of the haloalkane. So make sure it's a curly arrow. So as these electrons approach that partial positive centre, the bonding pairs of electrons around the carbon are going to be repelled away from the carbon. So this will repel there, that will repel there, that will repel there, and that will repel there. However, bromine is much better at attracting or accepting these electrons than the carbons or the hydrogens. So the most likely thing that will happen is that this bonding pair of electrons here will move to the bromine, and the bromine will accept the pair of electrons and become a bromide ion. And in the process, this covalent bond between the carbon and the bromine will break. So we also would see a bond form between the oxygen and the carbon, because this pair of electrons will be now shared between the carbon and the oxygen. So we have our products, and we've eliminated here a bromide ion when this carbon and bromine bond was broken. So just as a note, the bond breaking here between the carbon and bromine bond is heterolytic fission. So heterolytic fission is the breaking of a covalent bond, so you must mention covalent bond, where the bonding pair of electrons move to one of the atoms that was bonded, and the other atom that formed the bond has lost both the electrons. And we form ions in heterolytic fission. So also you can see that the equation is balanced in terms of charge. So at the beginning, the overall charge is single minus, because we have a neutral molecule here, has no charge, and we have a single minus on the hydroxide. And at the end, the products overall is single minus, because we have alcohol which has no charge overall, and we have a bromide ion which is single minus charged. So in an equation, we must balance in terms of atoms and charge. So we can draw a mechanism using skeletal form, which will be quicker in the exam. So it will be best to draw in this format, so you can see how this skeletal format relates to the display formula. So this will take a lot longer to draw in exam, so you won't have time to draw displayed. So, try to use skeletal to save you a bit of time in the exam. So as you can see, I've drawn a different version of this mechanism here, and it shows the shapes of the haloalkane and the alcohol. You don't have to draw this in the exam, but I thought you'd be interested to see that in the mechanism, the hydroxide ion attacks the carbon on the haloalkane from the rear, and as this approaches, it repels all these bonds forwards, pushing these forwards and pushing this bond, pushing this pair of electrons towards the bromine, and this bond breaks. And as the bromide ion is ejected out or eliminated, these bonds on the carbon hydrogens here and on this ethyl group here are pushed forward, a bit like an umbrella prongs in a strong wind, push far too far and inverts the shape of this tetrahedral. And this has a name. This inversion is called Walden's inversion, which you don't need to know for the exam, but I thought you'd be interested in how this actually happens. So that's all we're going to cover for this video. So we covered today the main reaction, which is hydrolysis. That is the splitting of a covalent bond or breaking of a covalent bond with the reaction of water. And we saw that hydrolysis is slow with water itself because water is not a very strong or potent nucleophile. So instead we use sodium hydroxide, and the hydroxide ions are much better at nucleophilic attack and attacking that partial positive center on the haloalkane. So we looked at the mechanism, which is nucleophilic substitution, and you can define nucleophile as an electron pair donor. So in the next video, we're going to look at how different haloalkanes will hydrolyze at different rates and different speeds due to their difference in carbon-halogen bond strength. And we can actually measure that and see that feasibly in a very simple experiment using silver nitrates, and we talk about that another time.